Hello everyone, myself Annu Kumari, BSc Chemistry Honors, third year. Today I am going to prepare an audio lecture for visually impaired student from Pradeep Physical Chemistry Volume 3. My topic is Raman spectra. General introduction. It is a special type of spectroscopy which deals not with the absorption of electromagnetic radiations but deals with the scattering of light by the molecule. It is observed that when a substance, which may be gaseous, liquid, or even solid, is irradiated with monochromatic light of a definite frequency, and small fraction of light is scattered. Rayleigh found that if the scattered light is observed at right angle to the direction of the incident light, the scattered light is found to have the same frequency as that of incident light. This type of scattering is called Rayleigh scattering. Professor C.V. Raman of Calcutta University, however, observed in 1928 that when a substance is irradiated with monochromatic light of a definite frequency mu, the light scattered at right angle to the incident light contained lines not only the incident frequency but also of lower frequency and sometimes of higher frequency as well. The lines with lower frequency are called strokes lines, whereas the line with higher frequency are called anti-stroke lines. Raman further observed that the difference between the frequency of incident light and that of a particular scattered line was constant, depending only upon the nature of substance being irradiated, and was completely independent of the frequency of incident light. If mu1 is the frequency of incident light and mu s that of a particular scattered line, the difference del mu equal to mu I minus mu s is called Raman frequency or Raman shift. Thus, the Raman frequency observed for a particular substance are characteristic of that substance. The various observations that made by Raman constitute what is Raman effect, and the spectrum observed is called Raman spectrum. Thus, in simple way, Raman spectrum may be represented as shown. Explanation for observing Rayleigh lines and Raman lines. When the incident proton hit the molecule, this collision may be elastic or inelastic. Elastic collision means that the colliding particle will return with the same energy. Thus, the scattered proton has the same frequency as that of incident proton. This explains Rayleigh scattering or Rayleigh lines. However, if the collision is inelastic, still the law of conversion of energy will hold good. That is, total energy before collision and after collision must remain the same. Thus, some energy may be transferred from the incident photon to the molecule so that the scattered photon has a lower energy and hence lower frequency than that of incident photon. This explains the occurrence of stroke lines. Alternatively, some energy may be transferred from the incident photon to the molecule so that the scattered photon has a higher frequency than that of incident light. This explains the occurrence of anti-stroke lines. This explanation may be further elaborated as follows. When the photon strikes the molecule, the energy is absorbed by the molecule and it gets excited to some higher energy level. Now, if it returns to original level, it will emit the same energy as absorbed, and thus we have Rayleigh scattering. However, in most of the cases, the excited molecule does not return to the original level. It may return to the higher level than the original level, thereby emitting less energy than absorbed. It may return to level higher than the original level, thereby emitting less radiation than absorbed. This explains the occurrence of stroke lines. Thus, a part of the energy of the incident photon remain absorbed by the molecule, so that the molecule has higher energy than before. Alternatively, the excited molecule may return to the lower level than the original level. Thus, more energy is emitted than absorbed. This explains the occurrence of anti-stroke lines. In this case, the molecule has less energy than before. The different cases may be represented diagrammatically as shown in figure 3.30. Level have been shown equally spaced just the sake of convenience. Article 3.37 Polarizability of molecule and Raman spectra. The Raman spectra arises and account of polarization, distortion of electron cloud of the scattering molecule that is caused by the electric vector of electromagnetic radiation. The induced dipole moment mu depends upon the strength of electric field E and the nature of molecule. We write mu is equals to alpha E, where the quantity alpha depends upon the nature of molecule and is called polarizability of the molecule. Thus, polarizability is the ratio of induced dipole moment to the strength of electric field. In case of atom or spherically symmetrical molecules such as CH4, SF6, etc., same polarizability is induced, whatever be the direction of the applied magnetic field. They are said to be isotropically polarized. Such molecules are said to be isotropic molecules. In case of all diatomic or non-spherical molecules, the polarizability depends upon the direction of electric field. For example, in case of H2 molecule, the distortion produced is more when the electric field is applied parallel to the bond than when it is applied perpendicular to it. We write alpha parallel is greater than alpha perpendicular. Such molecules are therefore said to be anisotropically polarized. Type of molecule showing rotational Raman spectra. A molecule scatters light because it is polarizable. Hence, the gross selection rule for a molecule to give a rotational Raman spectra is that the polarizability of the molecule must be anisotropic, that is, the polarizability of the molecule must depend upon the orientation of the molecule with respect to the direction of the electric field. Hence, all diatomic molecules, linear molecules, and non-spherical molecules give Raman spectra. That is, they are rotationally Raman active. On the other hand, spherically symmetrical molecules such as CH4, SF6, etc. do not give rotational Raman spectra. That is, they are rotationally Raman inactive. These molecules are also rotationally microwave inactive. In fact, this is one of the reasons for importance of rotational Raman spectroscopy or infrared spectroscopy, because of the light re- requires that the molecule must have permanent dipole moment. However, the former only required that polarizability of the molecule must change during vibration. Explanation of Raman spectra in terms of polarizability. The polarizability alpha of the molecule that is rotating or vibrating in constant but varies with the frequency of vibration or rotation. It is sum of two parts, which is first equilibrium polarizability alpha naught, that is the polarizability when the atoms of the molecule are in their equilibrium position. Second, sum of polarizabilities of the molecule due to various rotation and vibration motion, each term depending upon the frequency of rotation or vibration. Thus, alpha is equals to alpha naught plus summation of del alpha n alpha is equals to alpha naught plus summation of del alpha n by del r into Rn cos 2 pi mu n t, where alpha n is the polarizability associated with nth rotational or vibrational mode, and Rn is the maximum displacement of the atom involved. Further, the electric vector of the electromagnetic radiations vary with time, as E is equals to E naught cos 2 pi mu naught t. Substituting these values of alpha and n in equation 1, which is mu is equals to alpha E. Mu is equals to E naught alpha naught cos 2 pi mu naught t plus summation of del alpha n by del r bracket close r n cos 2 pi v n t cos 2 pi mu naught t. After solving this equation, we get E naught alpha naught cos 2 pi mu naught t plus half E naught summation of bracket del alpha n by del r bracket close r n bracket cos 2 pi mu naught minus mu n t plus cos 2 pi mu naught plus mu n t. This expression consists of three terms. The first term has the frequency of incident radiation and represents relay scattering. The second term contains mu naught minus mu n, and this represents stroke lines. Whereas the third term containing mu naught plus mu n, this represents anti-stroke lines. Article 3.38. The quantum theory of pure rotational Raman spectra of diatomic molecules. The selection rule for pure rotational Raman spectra of diatomic molecules are del J is equals to 0, plus minus 2. The selection rule del J is equals to 0 correspond to relay scattering, whereas selection rule del J is equals to plus minus 2 give rise to Raman lines as explained below. We know that the energy of rotational level with quantum number J is given by mu dash equal to bjj plus 1. When a transition takes place from lower rotational level with quantum number J to higher rotational level with quantum J dash, the energy absorbed in terms of wave number will be del mu bar equals to bj dash j dash plus 1 minus bj j plus 1. For the selection rule, del j is equals to plus 2, that is j dash minus j is equals to 2, or j dash is equals to j plus 2. We get del mu bar is equals to bj plus 2 multiply j plus 3 minus bjj plus 1 b 4j plus 6, whereas j is equals to 0, 1, 2, 3. Again for selection rule, del j is equals to minus 2, that is j dash minus j is equals to minus 2. J is equals to j dash plus 2. We get del mu bar is equals to bj dash into j dash plus 1 minus b bracket j dash plus 2 bracket close bracket j dash plus 3 bracket close is equals to minus b 4 j dash plus 6, whereas j dash is equals to 0, 1, 2, 3. Combining the result of equation, the wave number of the lines represented in Raman spectra will be given by mu bar is equals to mu I bar plus minus del mu bar, which is equals to mu bar equals to mu I bar plus minus b4j plus 6, where j is equals to 0, 1, 2, 3. Mu I bar represent the wave function of relay lines. Plus signs gives lines with higher wave number called anti-stroke lines. Minus sign give lines with lower wave number called stroke lines. For example, from equation 5, it may be seen that J is equals to 0, mu bar is equals to mu I bar plus minus 6b, that is first stroke, and anti-stroke line will be at separated 6b from relay lines. Further putting J is equals to 1, 2, 3, the separation between any two adjacent stroke lines or anti-stroke lines will be 4b. Thus the pure rotational spectrum expected for diatomic molecules may be represented in figure 3.32. Application of pure rotational Raman spectra. From the pure rotational Raman spectra, the separation between the lines, the value of B can be obtained, from which the moment of inertia and bond length of the diatomic molecules can be calculated as explained earlier. Quantum theory of rotational vibration Raman spectra of diatomic molecules. For larger molecules, the line obtained due to rotational transitions are so weak that they are beyond resolution. Hence, we have pure rotational vibration Raman spectra for which the selection rule are same as for pure vibration spectra discussed earlier. However, in case of diatomic gaseous molecules, the resolution of rotational fine structure is sufficient and can be studied. Thus, diatomic gaseous molecule give rotational vibration Raman spectra, which can be explained as follow. The selection rule for the transition are del mu is equals to plus minus 1, del J is equals to 0 or plus minus 2. However, at room temperature, as most of the molecules are in lowest vibrational level, mu is equals to 0. Therefore, the sufficient vibration transition is from mu is equals to 0 to mu is equals to 1, called fundamental vibrational transition. The restricting ourselves of to the vibrational transition only. The result obtained are as follows. Del J is equals to 0, del mu bar is equals to omega E bracket 1 minus 2xe bracket close, called Q branch. For del J is equals to plus 2, del mu bar is equals to omega E bracket 1 minus 2xe bracket close plus B bracket 4j plus 6 bracket close, called S branch. For del J is equals to minus 2, del mu bar is equals to omega E bracket 1 minus 2xe bracket close minus B bracket 4j dash plus 6 bracket close, called Q branch. Representing the values of Q, S and R branches by del mu bar Q, del mu bar S and del mu bar O respectively, and the wave number for exciting radiations by mu I dash. The wave number of stroke lines will be as follows. Mu bar Q is equals to mu bar I minus del mu bar Q. Mu bar S is equals to mu bar I minus del mu bar S. Mu bar O is equals to mu bar I minus del mu bar O. We have considered that the case of 4 del mu is equals to plus 1 represent stroke lines. The anti-stroke lines are those for which del mu is equals to minus 1. They are usually weak because very few molecules are in excited vibrational state initially. The rotational transition accompanying the vibrational transition from mu is equals to 0 to mu is equals to 1, and the rotational vibrational Raman spectra obtained by the represented as follows in figure 3.32. Article 3.42 Advantages of Raman spectra over infrared spectroscopy. Raman spectra has a number of advantages over infrared spectroscopy, as briefly explained below. First, since Raman frequency are independent of frequency of incident radiation, hence by the suitably adjusting the frequency of incident radiation, Raman spectra can be obtained in the visible spectrum range, where they can be easily observed rather than more difficult infrared range. Second, Raman spectra can be obtained even for molecules such as O2, N2, Cl2, etc., which have no permanent dipole moment. Such a study has not been possible by infrared spectroscopy. Raman spectra can be obtained not only for gaseous but even for liquid and solid, whereas infrared spectra for liquid and solids are quite diffuse. Because of the ease with which the Raman spectra can be studied, the molecular structure of large molecules of compound have been determined by Raman spectroscopy. However, infrared method still continues to remain popular. Article 3.43 Experimental arrangement for Raman spectra. The experimental arrangement for observing Raman spectra is shown in figure 3.33. The fraction of light scattered is so low that normally very weak Raman lines are observed. Hence, the defect that lines it is necessary to use a powerful source of incident light. Earlier, mercury vapor lamps were used, which give an intense monochromatic radiation of wavelength 4358 angstrom, which is 435.8 nanometer. However, with the development of lasers, which are very powerful source of monochromatic radiations, Raman spectroscopy has been greatly